Okay, again, so we are not going to meet on April 25th, and please, okay, just keep your uh, no, I'm sorry, upload your recordings to ELC on that day. And April 18th will be our Q&A. Okay, of course, you are very welcome to meet me before that day. Okay, just make an appointment with me because this is a small class. I can handle that. If we, yeah, in 1 year I have 30 students. I cannot meet every student, but for this size, I can totally do that. So if you have any question about your model, about your code, or about your, or maybe the topic, yeah, just please let me know. And course project, we will have a presentation and the final paper. So we'll have two parts. April 25th is a presentation day. So you don't need to come here, but you need to do your presentation. Okay. And the final paper will be due after 2 weeks. Okay. Between these 2 weeks, there's a reading day. So you're gonna write up your final paper between these 2 weeks. So again, please start it as soon as possible. Okay. Okay. Now is end of March, so you still have one month to do that. Okay, that's good time.
I know you mentioned how long is it going to be? You're about to say.
Yeah.
Right.
Yes. So for your presentation, I would like to see 4 parts. Okay, just like SEM1. So the first part is about introduction part. Tell me, why do you want to conduct that project? Okay, why do you want to address those research questions? Okay, the background, literature review, and previous research. Okay, so they might have some previous models, SEM models. Okay, so you can just do a brief introduction of those models and your research question. So what's the gap between the previous research and your own research? Okay, why do you want to fill those gaps? Okay, and the goals, your project, the goals. 1 point, okay. And for 3 points, it's second part, SEM model. So you have to, because this is SEM2, you must include latent factors. For SEM1, we didn't talk about factor model, so it's okay if we run mediation or moderation path diagram or regression, but this is SEM2. So if you don't have any latent factors, no, I will not accept your final project. Okay. And tell me your equation. Yeah, if you have any formula, for example, yeah, you have the yeah, this part can be flexible if you really don't need to, if you really struggle with this part, then maybe we can skip this part, but the path diagram should be included. So always, okay, path diagram is your model. Okay, it's kind of like a visualized version of your equations. So you can skip this part, but path diagram should be there. And also tell me, yeah, your method estimation part, yeah, the design part. Okay, so that's a model. That's the model part. And then you're gonna run your data analysis. This is another 3 points. Okay. So of course you can do either real data analysis or simulation studies, but this part is even harder. So I guess most people just want to run a real data analysis, because for simulation studies, so you need to generate your data by yourself. So it involves a lot of like other works. So we have real data analysis. First step, okay, descriptive statistics. What kind of variables you are going to include in your model? Sample size, means, okay, standard deviations, variance, something like that. Descriptive statistics. If yeah, you can also include some graphs if there's any. And then this is really important. So you have to include these 3 parts. Okay, so result tables. Estimate of your parameters. Okay, so what kind of like a parameters you want to estimate? What is the point estimate? What is the standard error? What is the ratio, C ratio or T ratio? What is the P value? So you have to include those result tables. and then do some interpretations. So what does that mean? So for example, beta 1, the coefficient from some variable to another variable is 1.2. So what does that mean? So you need to understand the meaning of those numbers. Is that significant or not? Okay, so to check the p-value. And then model fit, okay? So finally, you're gonna report some model fit indexes. So these indexes show, okay, showing that it's a good model or it's not good model. If it's not good, then you can also provide us some possible modifications. You can say that, okay, originally we don't consider that path. Okay, now we're gonna, based on the modification suggestions, we're gonna add that path, and that makes the model fit much better. That it's great improvement. That's a result part, okay, data analysis part. And the last part about the conclusions. Okay, so based on your results, okay, what's your findings? What is your finding? Okay, or what are your conclusions? And some discussion. So what is the limitation of your current study? Okay, what are your future directions? So that's a yeah, that's 2 points. Okay, yeah, that's 2 points. So add them together. We also have 1 point for presentation skills. Just use your body language or use your tones to show that you do a great job on the presentation. And please also include your references or appendix. So that's a structure of our presentation, and also it's the same for the final paper, and also for the journal articles, it's roughly the same. Okay, so we have 4 parts. Okay, and you may, and the great thing is that you may have these scores. Okay, if you did a really good job, okay, then it's excellent, 9 points or 10 points. Okay, 9 points or 10 points. And if you have some minor problems, then you may have 7 or 8 points. If you have some big problems, then 5 to 6 points. If your project is really, it's not qualified, you may have less than 5. So I will give you some warning message, and you're gonna revise it and redo your project. Okay, so this is the final paper. So the same 4 parts. Okay, introduction, model, data analysis, conclusions, okay, findings, discussions. Why it's conferences? I want to say what references maybe. References is already here. Okay, just delete this part. Okay. Okay. So APA style, just follow the APA style. Yeah, maybe I want to say that for different conference, the style may be different, but for the current project, maybe we're gonna follow the APA style. For different areas, the styles of the conference, different journal articles, they may have different styles. And again, for grading, if you do really good job, then you will have excellent, and then great or good or major problem. So I don't think that you will have these scores, because after you do the presentation, I will just stop you or just push you to go ahead. So if you made a really big mistake, then I will just ask you to revise it. So you will not have less than 30 points. Yeah, and as I said, that please just meet me if you have any question. Okay, so this is a relatively small class. So please use my office hours or use my other appointment. Just make an appointment with me, and you're very welcome to meet with me. And the summer, so this is the end of this semester. Okay, so we're gonna finish this semester in May. So in summer, if you really want to publish your work, okay, if you really want to submit to some conferences, then please let me know. So we can do it together. I can help you to improve the quality of the paper. And we can submit it to conference or journals, okay. And you can also take my independent study class. So it's from 1 point to 3 credit hours, okay. 1 point, 2 points, 3 points, it's up to you. During the summer, so we can improve the paper. So that's for course project. So the course project is just very rough draft of your, maybe your journal article or your dissertation or your thesis, okay? Because the time is so short, so we cannot do a lot during the course project for the, yeah.
What is the link requirements for both the paper and the presentation?
What?
The link. So like,
You mean the conferences?
no, so you for the paper,
Oh.
how long is the paper?
Oh,
review?
okay,
Minimum, maximum for length.
it's always hard to answer. You don't need to be long, but you have to clearly state these 4 parts.
Okay.
Yeah, but maybe after this semester during summer, you can just put a lot of like details into your paper. But for the course project, how many pages? I don't know. Depends on
How much does the introduction need to be? Do you want 46?
introduction.
No,
It's not our focus.
Okay.
Because our focus is your model and the data analysis. So introduction could be very short, including just your research questions and the reason why you want to conduct this project. Yeah, question.
Well, no, finish your answer. Well, I'm kind of going off of what she's asking.
Yeah.
I'm using data that I've already published. So it's already been published in the peer review article.
Data is okay. Data are okay, but not the model or because I want to do the SEM for if it's published.
I don't want to self plagiarize myself
Okay.
because some of that material I've already written that I would be putting in the paper for the class. That's what I'm asking.
If you have already published everything, just like the model and the data analysis, maybe that's not a good idea to do it again because you're gonna take this chance to give you another chance to develop more. Okay, you can change, you can modify your current model, you can add something new or
Sure.
just change.
I'll talk to you more
Okay,
about that after
yeah.
class.
Yeah.
How many minutes should the presentation be?
Around 10 or 15 minutes. Yeah, I will send an email before that presentation. Yeah, it should be short. Yeah. Let me see. Any other question? Yeah, most of us did the SEM1. So at that time we just did the presentation. Yeah. Face to face, and I will stop or I will just ask them questions if I think that this maybe need to be improved. But for videos, maybe I should send emails based on your presentation.
One more quick question.
Yeah.
If I pre-register most of the stuff I do, and the end is just gonna have the ultimate final paper that's coming out, it's gonna have more co-authors, and we'll send in on the pre-registration. As long as they aren't writing any of the main paper, is that okay? That people read it beforehand?
Yeah.
Okay.
Okay. So, yeah. The part I use red color is really important. Okay, you cannot miss any of these. Okay. So these are the extremely important parts. Okay. So let's move forward to our SEM class. So last week we talked about modification. So we can change our, question.
Just a question, on ELC, did you post this one up yet? I only see March 21st.
Oh, really? Okay, I'm sorry. I'm sorry. So let me just post it to.
The controversy is slack.
I thought I have already done that. Okay, so let me do this. Oh, yeah, you're right. We will have homework 5 today. Okay, so homework 5. Sorry, I thought I had already uploaded everything, so it turns out that yeah, okay, sorry. So we gonna, yeah, so last week we talked about modification. So based on the complexity of our models, we can have some relatively simple model, we can have some relatively complex model, and we can have nested models. And we can change the model a little bit. And if we start from a very relative simple model, and if we try to add a new path into your model, and that's called Lagrange multiply test. And we can clearly see the improvement. Okay, the improvement by adding some path. We can also do the test by reducing some path. That's called water test. And by using the code AM+, so including the test, they will clearly tell you if that change is significant or not. Okay, so we have different steps to do that. And the second session, we talk about the mean structure. So previously, we just focused on covariance structure. But SEM is about 2 parts, okay, mean and covariance. Although mean is not our focus, but still sometimes we need to look at the mean part. So we use a triangle with number 1 to show in our test diagram to show the mean part. And we covered 3 methods, okay, the algebra method and the tracing method and the RAMS matrix calculation to derive the mean part. Okay, so that's SEM with mean structure. And today we're going to apply the mean structure to a model called the latent growth curve models. Yeah, so we're gonna apply the mean structure. And the model is called the latent growth curve model. Okay, and of course we have a lot of examples. And the next session is about the multiple group analysis. So far, we just focus on one group. We didn't consider any different populations or different groups, but we can make the group as our new variable to make it different. Okay, so we have multiple groups. Of course, we have some examples. So for SEM, these are general equations. Okay, so if we consider mean, then we have this tau, okay, the intercept part, tau x, tau y, alpha. This is for x measurement, this is for y, okay, measurement of y, and the structure model. In most cases, we just, oh, okay. Yeah, in most cases, we just ignore the mean part. we're trying to look at the mean for today's class. So there's a model called the growth curve models. Okay, so or some people call the latent growth curve because all the intersected slopes or quadratic terms are latent. These are latent factors. Okay, so it's a bunch of like models. Okay, so they are a big family, a collection of models for investigating the change trajectory of phenomena or the mean change. Okay, mainly we look at mean change trajectory of phenomena. Yeah. So we're gonna investigate the overall trend of change of the whole population. And also we want to look at the individual differences of change among individuals, among participants. So let's look at the older data. Actually, we not data. Okay, let's look at the techniques. When we talk about factor analysis, we list different types of data style. Okay, data type. So we have 3 dimensions. We may have time dimension, we may have subject dimension, we may have variable dimensions. And by fixing some variables, we may have different names of those data sets. For example, we may have cross-sectional data or time series data. Okay, so for cross-sectional data, the time is fixed. So there's no variable in this dimension. But we can have a lot of like subjects, so the n could be large, and also we can measure a lot of like variables, so p could be large. So these 2 are flexible, but the time variable is fixed, so it's cross-sectional. And if we consider time series, then the time may have different. There are different points in this dimension. Okay, we have t waves or t time points, but usually we fix one subject, okay, one participant. Of course, we can measure a lot of like variables, okay, p variables, and different types of data. We have different techniques. So traditional factor models are technique, okay. Yeah, by fixing any of these 3 variables, and we can have 2 more. So let's look at the data structure or format. Suppose we have this format. We have different participants, 1, 2, 3, 4. Okay, so it could be 100 or 200. This is the sample size. And for each student, for each participant, we have different time points. Time point 1, 2, 3, 4, different waves. This is called wide format because it's quite wide. For each participant, we have so many different time points. It's wide. So let's look at the example. Actually, we use this example a lot. So we choose different time points this time. So previously we just focused on the first time point, okay, HVLTT at 1, LS at 1, LT at 1. But actually there are 6 time points. So we're gonna choose some different time points to do the data analysis for today's example. So this is a plot, a longitudinal plot. Okay, so
Sorry.
So we have
Thank you.
different time points. Suppose we focus on the memory test. Okay, HBLTT is a memory test. We have different test time, and in the very beginning, so we have these scores. And the second time we have the other scores. Okay, third time, and if you just connect those dots, we have spaghetti plot. It's also called a spaghetti plot or trajectory plot or longitudinal plot. Yeah, we have different names. So we try to look at the trend first. Okay, we're trying to look at the overall trend. And then also we're gonna look at the variance and the covariances among them. So this is a model. Okay, so we have different time points. So the time is a covariate in our model. So the observed variable y, the test score here, HBLTT test scores here, we assume that, okay, so we have latent intercept and the latent slope. So those two variables are latent. And we have time as our covariate. So it's kind of like the model to describe the overall trend here. It's linear or it's non-linear or yeah. So if we use a matrix form, say we have 3 points. Of course, in the data analysis, it's not 3. But if we have example, say T is 3, then we have y for individual I observed at T1, y, okay, the memory score, the HBITD score for individual I tested at level time point 2 and time point 3. And then we have if you combine these together, okay, so we have the 1 and the time and 2 columns. And the 2 parameters, beta 0, B0, and B1 are parameters beta. This is our X design matrix. Okay, the first column is 1. And then we have time. Time point 1, time point 2, time point 3. And the first column is 1, 1, 1, 1. And we have 3 residuals. That's it. This is the matrix form for the growth curve models. And these 2 are latent. We don't know the intercept, we don't know the slope. We just want to estimate those parameters. Yeah, as I mentioned, we have 2 parameters. B0 is intercept. So for each observation, so here we focus on I. So for each observation I, we have their own intercept and we have their own slope. Okay, so it's based on I. But the design matrix, the X matrix is fixed if you check the design matrix again. Because we know the time points, okay, we know it's day 1, day 2, day 3, okay, so or year 1, year 2, so we know the time points. So this matrix is given, this is known. But in addition to that, we also assume that we have the average of all intercepts. And we also have the average of all slopes. So these are independent with I. Although for each individual, we have their own intercept, we have their own slope. But if we take the average of all individual BI0, so we have beta 0. This is average. This is independent with the individual score. Okay, so we assume this is a mean structure, okay, mean structure of intercept. This is the mean for the slope. And of course, we are going to look at the variance of the B0, variance of B1, covariance between B0 and B1. So interaction between the intercept and the slopes. And there's a variation of, just like here, okay. So assume that we have some general trend here. So what is the variation of the intercepts? And we may have different slopes if we assume it's linear change. So what is the variance of the slopes? Okay, is that big or is that small? The intercept is very small. We're gonna look at those parameters. Then, in summary, we have these equations. Okay, for each individual, we have observed value of y for individual I, okay, based on different time points. We have the equation here. And for all of these intercepts, it's coming from this equation. So we have average score and their individual variation. Okay, so this is a residual for individual I. Okay. And this is average of the slope, and this is individual score. This is you can think about this residual, the unique part of that individual art, slope. Okay. In addition to the average score, they also have their individual slope. So that is VI1. And we may have, we can have different types of the growth model. So the first one is a very simple one. It's just no growth model or the flat model. Nothing changed. Okay, so based on this model, there's no pattern. The pattern actually is no change, no growth. And then we can also have a linear growth. We can have a quadratic growth. We can also have, you can make this larger, okay, cubic growth. You can make this larger. And also we have a latent or basic growth. So I will show you the differences among them. So no growth model, it's very, very simple. That's it, no growth, okay? So the data trend is just like this. We have no slope, but the individual part still have the variation. So the slope is the same, no differences among their slopes. But the intercept, okay, the intercept, I'm sorry, so beta zero part are different. So if we have the pair diagram, it's just like this. So we have so we have 3 time points, okay? 1, 2, 3 time points. And then we have their latent slope, okay? So we have B0, okay? And we don't have the slope. If B1, we assume B1 is 0, okay? This is flat, okay? And we have the residual, okay? So this is a pattern. This is a very simple case, okay? And the coefficients, okay, the coefficients is also fixed because this is just average, okay, it's the average of each. But we can make it change, we can make it different by adding the slope. So we have another latent variable here. It's B1, okay, so we have the B1. So in this case, it's just like this. In addition to the mean part, we also have the rate of change. Rate of change. This is for time point 1. Okay, time 1. This is time point 2. So we have some coefficients because based on the model here, we have some coefficients. We have different time variables. Those are coefficients. Time point 1, time point 2, time point 3, and the times the b value, and the coefficient for the intercept is just 1, okay, 1, 1, 1, 1 times the b0. So we have, of course, we have the residual part, and we have the observed part. With the different time points, we have the value of the y. In addition to this, we also want to invest the variance of the intercept, okay, the variance of intercept or the variance of slope and the covariance among these two. So you can think about this. Sigma 1, 2, this is sigma 2 squared, sigma 1 squared. What is the association among these two? What is the variation of the intercept? What is the variation of slopes? That's linear. And we can make it more complicated by adding one more parameter. This is quadratic, this is curve. And the model actually is quite easy. We just add one more term here. We just add a quadratic term here. Okay. And then the coefficients become what? Because it's quadratic, okay, so the coefficients become squared of the time point, okay, time point 1 squared, okay,
And then second one is time point 2 squared. This one is time point 3 squared. Because the equation could be like, becomes like this, okay? So the intercept here, I'm sorry, the intercept here, B, okay? And this linear term, that means the power of the time is just linear, it's 1, okay, linear. And then we have quadratic term. The quadratic, why it's called quadratic? Because the power of the time t comes second, okay? And we have the residual part. So the coefficient becomes time squared for the B, I'm sorry, this is B2, I'm sorry, this is 2. The coefficient for the quadratic term becomes squared time points. And the linear term is here, linear. And the first term is just constant, okay, because it's the mean part. Because now we have 3 latent factors. These are all latent. So we have the association among them, okay? Also the variance of this part and the association for the relationship among them. Okay? Yeah, that's it. So we have 3 covariances, 3 variances among these latent factors. So we have 3 by 3 matrix. That is for phi, okay? And of course, we have the residual, okay? We have the variance for the residual part. This is sign matrix. This is a sign matrix. Phi matrix, sign matrix, and the coefficients are all known. That is for the growth models. Okay. And as I mentioned, you can, of course, you can increase the power. You can just continue the polynomial. This is called a polynomial to make it a cubic term or other. So you can add 1 more or 2 more latent factors here. And of course, the dimension of the phi matrix and sign matrix will increase. But we will just stop there. But let's look at another type of model called the basis growth curve models. So in this case, we don't fix the time values, okay? So we assume that some time points are estimable. Okay? So we can change the time values like starting, for example, we can make it the very beginning part 0 to 1, okay? And then we can estimate those parameters. Okay. We can also, we can estimate those parameters. We have this, yeah. So I will give you the code. You will see the difference between the current model and the previous models. So the data trend may not be linear, may not be quadratic. It depends on your data. Okay, the data decide the trend. Okay, so let's move forward to the actual example. We have the HVLTT at different VLTT scores at different time points, and then we're gonna try all of these. Okay, and do the data analysis. So in M plus, it's quite easy. So we have title. Suppose this is a title for no growth model. We have data file. This is data file. Variables. So we use 5 waves of the HVLTT test, memory test. We're gonna use all of these. This is our model. Okay, so for latent growth curve models, it should be very simple. It's very simplified as this one statement. This is B0. Okay, intercept is measured by, okay, we have HBLTT1, the coefficient fixed at 1. So remember that for the no-base model, all the coefficients for the intercept B0 is fixed at 1, 1, 1, 1, 1. So this is a latent variable, okay? So latent variable is measured by the first wave of HBLTT, the coefficient fixed at 1. The second measure of HBLTT is the coefficient fixed at 1. Third wave fixed at 1. Fourth wave, fifth wave. All that means the coefficients, 1, 1, 1, 1. Okay. So that's it. This is and we didn't mention B1, B2. Okay, this is just B0. B0 is the intercept, no growth, just the average part. If it's linear, we add one more parameter. Okay, so the same beginning part, 5 waves of data. Now we have linear, so we add one more parameter. Okay, one more factor. B2, I'm sorry, B1. B1 is the linear coefficient. In addition to the mean part intercept, we have the slope, B1. And again, this is measured by these 5 waves. But let's look at the change of the time. Okay, so it's not 1, 1, 1, 1 anymore because the coefficient for, we assume that if it's linear, so let me make it linear. So this is 1, 1, 1, 1. Okay, from here to here it's 1, 1. Because we have 5 waves. We have 5 waves. So all of these are 1. But for B1 here, this is the slope, B1. We assume, okay, this should be the time points, okay, from here, here, to here, to here, to here. These coefficients should be different time points. Okay, but looking at the original data set, we'll assume they are equally spaced, okay? So from 0 to 1, from 0 to the very beginning, from the very beginning to the last time points, we equally divide the time points, okay, with the same space. So we have 0.25, 0.5, 0.75. So we have equally spaced 5 time points from 0 here, and the 0.25 here, and the 0.5 here, 0.75 here. It's 1 here. This is our rescaled time. Of course, you can use 1, 2, 3, 4, 5. It's the same. Okay. If it's not equally spaced, then you can just change the space to different actual time points. Okay. But assume it's equally spaced and we use this rescaled value, then it's the coefficient fixed at 0 for the first time, initial time points, okay? And then we initial time points, okay, starting from 0, and then we ended at 1. And then we have 0.5, 0.1, 0.7, 0.75, finally it's 1, okay? That's a code for linear change. And if it's quadratic, we need to add one more. Okay, suppose this is the quadratic term, quadratic coefficient, B2. Again, it is a latent factor. By using vertical bar, we think that it's kind of like a measured by. Okay, measured by. This is also measured by these 5 waves of data. And check the coefficients. It's the same. We didn't use a squared term, because M plus automatically know that this is a quadratic term, and they will automatically square those values for you. So it still keeps 0, 0.5, 0.25, 0.5, 0.75, 1 here. Okay. So they will change the actual coefficient for you. So very simple. That's it. Okay. So let's try to run these 3 codes M plus. I'm sorry, I didn't upload the code, so let's just do the exercise. I have some notes here, so this should be good. So let me just upload the code. Let's see. Okay. Data files at HDLTTM plus, and then we have vertical model 0, 1, 2. Okay. So, just ignore the comments. I have some comments with a green color. So those are modifications. Just ignore in the very beginning, just ignore those comments and we will just change the model a little bit.
So I can't read that if you're expecting.
Oh,
me to
yeah, I
read
will
that.
make it larger. Yeah, I will make it larger because I'm gonna change it. So this is a 0. I will make it 5. Okay. Yeah, please first ignore the green part. So B0, we have the mean, which is measured by these 5 waves, and the coefficients are fixed at 1. So just click 1 to see what's the result. So these are results. The repeat of the input file and make it a larger. So the repeat of the input file here, and then the data information here. Yeah, we have number of dependent variables. We have five waves of data. So well, HDLTC 1 to 5. No independent variables because it's just the observed dependent variable. Okay, one continuous latent variables. B0. Okay, B0 is a 1. Okay, B0 is a latent mean. Okay, and we have this 5 continuous output. And the algorithm and the descriptive statistics of each variable here. And then the model fit. Okay, those are model fit in boxes. See, actually, this is really bad model because we assume there's no change at all. So based on the RMSEA, it's 0.2. Okay, and also CFI and the TLI 0.8, 0.8. Those are not good indicators. This is also big. Model result. See, the coefficients are fixed. B0, which is estimated by this, not estimated, measured by these 5 waves of data. All the coefficients are fixed at 1. So we don't have standard error. We don't have the p ratio. We don't have the p value because this is fixed, the constant. And then we have the B mean. Okay, let's say this is the mean of the average, okay, because now we look at the average. So the average of these 5 intercepts, okay, intercepts, okay, average. And the variance, okay, the variance of the mean part and the residual part, okay, the residual part. That's it. This is our no growth model. And then let's look at the linear growth model. So linear, it's GCM 1. Okay, so this is the code for linear. We only needed to add one more parameter here and change the coefficient from 1 to those equally split values. Okay, that's it. Just trying to click run. And we have the results. Here we have some problem, warning message. Although the model estimation terminated normally, but we have some warnings. So it said the latent variable covariance matrix psi is not positive definite. This could indicate a negative variance occurrence residual variance, okay, for latent variable. So let's see. Here, this is a problem. Okay, so let's check this model. The variance of slope, okay, this is the intercept, this slope. The variance of slope, it's negative. So obviously, this is a huge case. We need to think of this model. Okay. So this variance is negative. It's not quite correct. So that's why we have the warning message here. Problem involving variable V1. Okay. So this also kind of like a debugging information for us. We're gonna read and figure out where is the problem of the error of the estimation. And when you check the RMS still it's quite large, and the CFI, PRI quite low, lower than 1. Okay. It's also 1. And the coefficients are fixed. Coefficient for mean part 1, coefficient for the slope. Let's look at the slope, the coefficient. It's fixed from 0, 0.25, 0.5, 0.75, 1. Okay. We don't need to estimate all of these coefficients. But we do have the covariance between them. Okay, B1 is in slope, B0 is intercept. We have the covariance between these two variables. And the variance, okay, and the variance of intercept, variance of slope. Of course, this is wrong information. And residual variance, okay, for each wave of these 5 data, we have the residual variance. And then we also have the mean part of the average. This is average intercept, average slope. Now let's look at the quadratic model. Quadratic model is GCM2, okay? GCM classical model 2. And this is the only difference between the linear model and the quadratic model. We just add one more parameter, quadratic term, and we didn't change the right side. So that's wrong. Results are here. In this case, we don't have any warning message. That's good. Okay, it just only show the estimation terminated normally, and that's good. But still, the value of RMSE is big, and these are better than the previous 2 models, but still, it's yeah, it's at least it's 0.9, okay, still not very good. And let's check the coefficients for the mean part, fixed, 1, 1, 1, 1, 1. Okay, for the linear part, that's it. For the, let's look at the quadratic part. This is squared version of these 5 waves, okay? Squared 0, 0. Squared this value, okay, here. Squared 0.5, 0.25, squared this value, and also squared value. So this is a squared term. That's why it's called a quadratic term for the coefficient. And it also gives you a lot of like covariance, okay, 6 covariance, or 3 covariance and 3 variances, 6 together, okay. So 3 covariance, intercept with slope, that's it, okay. And quadratic term with intercept, quadratic term with slope, okay. All of these are covariances. And we have variance for intercept, variance for linear coefficient, variance for the quadratic coefficient. Of course, we have the okay, and the residual variances. So it seems that the results are not quite good, and we can try to modify the model. And before we do the modification, we can also look at this new model. Okay, so here we trying to delete the time points. Okay, so here this is called a basis latent model. So we still assume it's linear. Okay, we have intercept here, we have slope here, but here this is a change. We don't fix the value, the coefficient value at these time points. Instead, we free these parameters. We want to estimate those parameters. So that means the time points here is not fixed. So we want to estimate those time points. Okay. And why do we have another value after the little star here? So that means these are starting values. We assume these are starting values. And then eventually they will provide the estimate of those coefficients. Still assume the time is from 0 to 1. Okay. Let's run this model. You can just modify it a little bit, but where's the code? Let me see. Any code? You can easily modify the code and save it to a new one. Now, let's just modify the code by adding choose a GCM linear 1 and save as to another basic model. And add asterisk here by removing the X sign. Really estimate those parameters coefficients. So this is the new result. Now let's look at the RMSEA dramatically decreased. Okay, although it's still larger than 0.05, but it's less than 0.08. And these two indicate that the model fits the data quite well. So let's look at the code here. From 0 to 1, we change the parameters here. So we don't assume this is linear. We base on the actual data and then estimate the coefficients. Okay. Coefficients are different. And also we have the covariance between them. The covariance between the slope and intercept, and variance of intercept, variance of intercept, variance of slope, and the sign matrix. Yeah, so that's a difference. So it's not linear anymore. But the pattern actually is based on the actual data. Okay, it's not linear, it's not projected, it's not no growth. So here I provide you a table, so you should be able to figure out how to finish this table. So we have no growth model, linear growth model, project growth model. Well, you can call it although it's called a latent, or you can call it a basic model because all the coefficients are latent. Okay. So we have the coefficient here. I use beta, but you can also use B. Okay, B is the intercept, or you can use B. Parameters, the population parameter is beta 0 and the beta 1, beta 2. So the coefficients are in the plus output. And here, this is the phi. Okay, phi table. What is phi table? So we assume, just like the vector model. So we have y, we have lambda, f, we have e. So the latent factor here, okay, latent factors here, the f. So the variance of the latent factors, we assume it's phi, okay, or phi. So in this case, if we assume there are 3 factors, so we have f1, this is a vector, okay, so we have that f1, which is beta 0, okay, beta 0, beta 1, beta 2, then the covariance matrix is 3 by 3, okay, is 3 by 3. So we have P11, so this is called P matrix. P22, P33. And we also have the covariance among them. P12 is a covariance between intercept and the slope. Okay, so this is 1, 2. P13 is the variance, the covariance between intercept and the projected term. The whole matrix is called P matrix. And we also have the P23. So this is the covariance between linear term and the projected term. Okay, so we have 6 components. So that's why in the table we have 6 components. P11, P12, P22, P13, P22, P33. All of these is from the phi matrix. Okay, the variance of latent factors. So what does that mean? This is the variance of the intercept. This is the variance of slope. This is the variance of projected term. Suppose we have projected term 3 terms. This is a covariance between intercept and the linear term. Covariance between intercept and the projector. This is the covariance between the linear term and the projector. matrix. But in addition to this, we also have psi matrix. What is psi matrix? As I mentioned, we have the y, okay, lambda f plus e. So the residual part, this is the residual part. We just mentioned the variance covariance matrix of F, which is phi, and this is the variance matrix of F. How about the variance matrix of E? We use psi. Okay? Psi is a covariance matrix of E, and we assume it's independent. All the residuals are independent. So the psi is diagonal elements. Okay? Diagonal elements. We have 5 waves. So we have psi 11, psi 22, psi 55. Okay. We have 5 waves of HVLTT. Okay. Residual at 10.1, residual at 10.2, variance of residual at 10.5. And it's diagonal, so all the off-diagonal elements are 0. So that's a psi. So together, this is a psi matrix. And this is the phi matrix. Okay. This is the variance of F, this is the variance of the E. And together, we have the covariance matrix Y. We use a capital sigma. And the capital sigma is the combination of this, okay, lambda matrix times the P times the transpose of the lambda matrix plus psi. Okay, this is a combination of all of these components, 2 parts. Because we have the matrix here, so this is a combination of this. This is a psi matrix. This is a sigma matrix, combination of these 2. So all the parameters are listed here. So we have psi 11, psi 22, psi 55. And of course, for growth, okay, so we don't have, for growth, we don't have a lot of information. We only have the intercept, the mean of the intercept. Let's have this table. For different model, we have different number of parameters. So for the no growth model, we don't have the information for linear average for linear part. We don't have the information for average of the projected part. And we have this C11, which is a variance of the intercept. We also have the average of the intercept here. So this is the mean. This is the average mean value of the phi 0 I. Okay, this is the mean value for phi 1 I. This is the mean value for phi 2. So we don't have this information. All of these are missing because we don't have the in linear part and we don't have the major part. But for psi, it is there, okay? So for psi, we have this information. For linear chain, we do have the information of this. All the psi matrix is listed here. Okay. All the information, the elements of psi matrix are listed here. For quadratic, we do have everything. Okay. We do have all of this. But for the last one, because there's no clear pattern. Okay, for the last one, we still have the estimate. Okay, so we still have the estimate of these terms. Okay, but it's not quadratic, so we have, and we still have these terms. Okay. So that's the output of our impulse. Okay, that's one part. If you do the course project like this, you need to provide us a similar table like, of course, it depends on your model. So if you really want to run these 4 models, then that is the result table you want to provide. But if you just want to run linear and the projected, then these 2 columns will be enough. And also, you need to provide the model fit indexes. So here again, I chose 4 models: no growth, linear, projected, latent, and chi-square values, degrees freedom, p-value, RMSEA, SRMR, SPLC. You can make it longer. Okay, so you can put more information if you have any other model fit indexes. Yeah. Based on these 4 models. Okay, yeah, let me just make it bigger. Oh. I cannot change here. This is cannot change here. So you can just make it larger, longer by including the CFI and the PLI information. Anyway, so let's look at the results. For linear, there's an error message, there's a warning message because the variance is negative. So the results are not trustful. So we just delete the result for linear model. We don't want to consider that model. The results are not reliable. Okay? There's a negative variance. So that's it. So comparing no growth, quadratic, and latent or basis model, which one is the best? Yeah, the last one seems good because all of this seems very big. Okay, although this one is still big. Okay, this one is still big. But if you do the comparison of the AIC-BIC, okay, for AIC-BIC, smaller the better. So this is okay. 31,000. Okay, this is 30,000. This is also 30,000, but this one is smaller than this number. Okay, this number is smaller than this number, and of course, this is the largest one. AIC-BIC, okay, because these are messages, so this is the smallest one. We're gonna choose the last model. Okay. So in your course project, if you want to do some model comparison, so you can just provide some competing models. You don't know which one is good, the best one. So you just list the results, the model fit results, just like this, and you do the comparison. And if you chose this one, please clearly say why. What is the evidence to support you to choose this one? Okay, this is the best fit model. Why? And you can say something to support your conclusion. But still, okay, the one seems not quite good. So we can do some modification. So we can modify our model. For example, this one seems the best among these 4, but still not. It's for example, what is the RMSE is a 0.7, yeah, 0.07, still it's quite large. So we can add the modification, okay, mod indexes to see if we can improve the model. So let's look at the code here. Here, we didn't use some starting values. So starting values is optional for you. You can, just like we did in the previous case, you can add a starting value after this little star here, asterisk here, okay? But you can also remove that. It's totally fine because this just provided some actual information for estimation, okay? And if you look at the code here, we don't have the, yeah, here we have 1, but here we don't have any starting values. It's totally fine, okay? And suppose we have the 3.84. This is a number, the critical value of chi-square with first degree freedom, with degree freedom 1. Okay. Let's try to modify our model. Then, yeah, so let's just add this statement into our code. Again, please ignore this part because this is a suggestion we want to add, but please just ignore this comment and then try to look at the modification. Okay, so run the code. So it should be a new model. So save as, let's say this is modified. Then click run. So everything should be the same. But finally, we have some suggestions. Okay. That is a suggestion. Okay, this is a model modification indexes. So this is suggestion. Let's look at the meaning of that. Okay, so the software suggests us might include each or any combination of these statements. By statements, okay, B0 by HVLTT2. So what does that mean? So B0 is already estimated by HVLTT2 because B0 is vertical bar by 1, 2, 3, 4, 5. So it's already there. So you can totally ignore this statement. B0 by HVLTT5. Then it is there, okay, because we use a vertical bar in the very beginning of the code here. This is measured by, okay, this means, okay, measured by these 5 waves. So this statement is already there. Ignore this part. And then we can also consider the on or by statement. What does that mean? Okay, B1 on B0. So the slope is regressed on intercept. So that means the intercept here, intercept. Oh, I deleted that. I removed that. Intercept gonna influence the slope. Okay. So this is one part of the suggestion. And also B0 by B1. So what does that mean? B0 is measured by slope. Okay. Just the same direction, but the different statements. Okay. But still, we assume they are correlated. Okay, intercept and the very slope are correlated, but not directly cause. Intercept gonna influence the slope. That is the meaning. So we will just see. Okay, so let's look at the way statement. Okay, way statement. What does that mean? HVLTT5 with HVLTT4. With means correlated. Okay. There's an association between HVLTT5 and HVLTT4. Of course, this means the residual part. Okay. This is interesting. So if we have the diagram, so if we have the let's quickly draw the task diagram here. So from 1 to 5, okay, HVLTT. We have all of these procedures, and we have the intercept. We have all of B0, okay. And we have B1, okay, and we have all of these. Here we have 0, and we have 1, and these are estimated our data. So it means this suggestion means what? Okay, so HVLTT5 and 4 are correlated. We can assume these two are correlated. Okay. So the fourth wave and the fifth wave's data are not independent. That makes sense. So this makes sense. So we are going to take this piece of information. So the change of the modification indexes will be 11 point, which is larger than 3.84. So it is significant because if the value larger than point chi-square value, critical value with 1 degree freedom, it is significant. So this is a good suggestion. We're gonna modify our model by adding this statement. Okay, by adding this statement. And of course, there are some other statements about means intercept threshold. Okay, so HBLTT2, the main part, that does not make any sense. So we are going to add this statement in our code. It becomes this one. Okay, so if you delete the comment sign, okay, then this is a new code. HBLTT4 and 5 are correlated. Let's try to run it again. This is the newest model. So let's see. It's not. Okay, now let's see the RMSEA. Yeah, it did decrease. Okay. And this one also becomes smaller. Okay, this is less than 21. The previous model is still larger than 21. So this is less than the previous RMSEA. And for these two, are still quite close to 1. AIC, BIC, these are quite close, I think. So we add a covariance between HBLTT4 and 5. Right? Yeah, this is a new model. So new model, I just show the past diagram. It's correlated and plus code and plus the results are here. Okay, this is the results. Coefficient for the second wave and third wave for the fifth wave are estimated. And the covariance between mean of intercept and the slope. Okay, it's here. Yeah, this is a association between them. Okay, the covariance between them. And the average of the intercept, average of slope, variance of intercept, variance of slope, and the residual variance. Yeah, we have already taken that information. Actually, they have some other information, so you can also consider the covariance between 1 and 3. Okay. So maybe we can continue to do that if we add one more statement, 3 and 1, see what's the change. Okay. We can. Now we have some error message, so we cannot continue. So again, the sign matrix is not a positive definitely. So let's see the sign matrix. It looks good, but still the variance. Okay, now this is the problem. Okay, the variance of the intercept becomes negative. We cannot use this piece of suggestion. It becomes worse. So we just stop here. We delete these comments. Okay? These comments does not make the modification better. Actually, it's worse. So we still use the previous results. This is the results. So how to understand the meaning of this average or covariance? Yeah, how to understand the result tables here. So we can do some interpretation. like this. And in your final project, you need to add this statement, okay, to do the interpretation. For example, in this case, okay, we want to know the average initial level of HVLTT score at the beginning of the study. So average, the initial level of the HVLTT, which is the mean, the average of the beta zero, okay? Beta zero, what is the average of beta zero? If you go to the result here, it's B0 here. This is the B0. This is the average. This is the average mean, okay, of the intercept beginning of the HVLTT scores. This is the average. So it's 27.448. And the standard error here, the P ratio here, it is significant, okay? So you can just answer the average initial level of HVLTT as a beginning level is, and then you can continue, okay, the standard error with, okay, with standard error equals some value and the P value, yeah, 0, P 0, okay. We can continue this part. Just to, yeah, to indicate that this indicates that this is significant, okay. And the variance of the initial level of HVLTT, okay, the variance, let's go back to the results. We're gonna check the variance of B0 here, okay, here. The variance of the initial level of HVLTT score. The intercept is 16.74, and the standard error and the p-value. The variance is 16.74, and the p-value. Okay, of course, you're gonna continue. Okay, with standard error, some value, p-value. Okay, because so there's a significant individual differences in the initial values because the p-value is significant. It should be 0. And also, let's check the slope. Okay, the slope. The average. Okay, this is the slope. This is average slope. Okay. Mean of B1 slope. But what does that mean? So 1.210. So this is a change in the Y score when time has 1 unit change. Okay. So this is but the time has already been fixed from 0 to 1 here. So if we have 1 unit change, then the average of slope is 1.210. So the difference between the first measure, okay, starting 0. The first measure we start at time 0, and the last one we have 1 unit change from 0 to 1. The differences in Y is 1.210. And also, we're gonna add the standard error, the p value. Okay. It's significant, I think. Yeah, so it's significant. The variance part, okay, the variance of the slope, okay, the variance of slope here. This is the variance of slope. The variance of the slope. And this value, standard error here, ratio, and the p-value. P-value is not significant. Okay, let's check this p-value is not significant. What does that mean? So the variance of slope is not significantly different from 0. So you can think that the slope is quite stable. The variation is not so big. Okay, it's not significant. So you can think about it's quite constant. It's quite constant around this value, 1.210. The variation is very narrow. Yeah, the p-value is larger than 0.05. if we do the upper levels on the 0.5, it's not significant. So that means there's no individual differences in their slopes. So the change of the slope is quite small. It's not significant. The variance is the change of the slope. This means the slope is not significant. So among different individuals, the change is not significant. And also we can check the covariance between them, covariance between intercept and slope. Let's go back to the covariance part. Here, okay. Intercept, this is a intercept, this is slope. The covariance, again, it is not significant. So the value estimated, the point estimated value, the standard error value, the p value, is not significant. So the intercept and slope are quite independent, okay? So there's no significant association between them. Yeah, so the initial value, which is intercept, is uncorrelated with the change, the slope, okay? The slope, the change. The value is not significant. Yeah, so based on the result, you should do some interpretation, explain the meaning of those numbers, and that makes sense. Okay, so we're gonna use a daily language, the common language to explain those numbers. Okay, especially you should point it out it's significant or not. So that's for the example of linear growth curve models, and you do have homework 5. Okay, homework 5. I give you another set of value, not actually LTT anymore. So it's EPT. Okay, so I will give you the data, and then you're gonna run these models. You're gonna run no growth model, linear growth model, projected growth model, and the basis latent model. Okay, so 4 models. And then this is 3 points. Okay, these are 3 points. And then you're gonna select the best fit model. You're gonna do the comparison. And of course, explain why. Okay, for example, you're gonna select the linear. So why do you want to select linear growth model? So you should provide the table of model fits, okay, and explain why. And then you can also do model modification based on that best model among these 4. Okay, 1, 2, 3, 4. You can also do further modification at one point and show the table of model results, okay, and do some explanation of the results. So that's 2 points. And please provide your code and the important results. But results, it could be really long, so please do not attach everything. Okay, just give me the important results. A model fit results, and the model results. Okay. Yeah, so that's homework 5. Oh, we also have homework 3 and 4. Okay, so now it's 7. We can talk about homework 3 and 4, EF and CF in the beginning of next session. Okay. So this is the homework 5. Any question? Yeah,
So
question.
homework 5 has to be done with N plus, because that's all.
Yeah, that's very simple. Yeah. Okay. Any question? Okay, then we can have 15 minutes break, and we're gonna look at the multiple group analysis. Okay, yeah. Thank you.
Hey, we all get A's, right?
Yeah. So I think that's it.
Hey, I got that over quick. Okay.
So this is my homework. Yeah, so that's all just setting it up, importing it in, getting my correlation matrix ready for the eigenvalues.
Oh, you should talk about the beginning part.
Oh, all of it.
Eigenvalue on what? Eigenvalue on which matrix?
Oh, I'm not that good.
So eigenvalue on what kind of matrix?
You don't do that till later on, right? When you're talking about the
I'm
matrix.
setting it
Yeah.
up for the eigenvalue.
Yeah,
Yeah,
If it was raw data, it wasn't.
right.
yeah, that
Because
top's
we do have
wrong.
some different solutions, so eigenvalue on which matrix? Yeah, it's correlation matrix, yeah, it's,
That's
yeah.
next.
okay.
Yep, so then just got my eigenvalues set up. And these were what returned for me. So 2, and we'll see on the ski plot as well. So I ended up going with 2 to begin with. So I checked that with the actual plot. So let's scroll down. So original plot, just like we did prior, and then ran the parallel analysis as well with that. So it showed 2. So I chose 2 originally, and I went back in the end and chose 4 because the 2 wasn't very good, and I know they're under the cutoff. Some of that would be theoretical underpinning. I didn't explain that on there, and she asked why did I go back and do 4. It'd be kind of theoretical underpinning. I also felt why they felt under there. Go back to the original eigenvalues. There was a pretty big cutoff here, so it was truly just like a theoretical underpinning and curiosity on my end, since it was homework, to see what would happen if I chose 4. So went ahead and did move forward with the 2-factor analysis, or the 2 latent variables, excuse me, for my factor analysis. And then I went through and started with the no rotation. And got, yeah, so did all the different rotations. So I'll just jump to what I used. So I'll go back and talk about the data in a second. So with no rotation, it was a poor model fit. I ran kind of the same thing with the very max rotation. So I went with the pro max rotation, which came up with the best factor loadings here by and large. So I did put the 2 factor on there. So that's my 4-factor loading, sorry. Here's one with 2. So this was not with the, sorry, Pro Max, this was with the very max rotation. And that wasn't very good factor loading. So I did the original 2 with the Pro Max rotation, but then overall the model fit was pretty poor. So then you can see out of curiosity / kind of just knowing what this is supposed to be measuring, this test, just from what we do in Psych, I was curious what would happen if I added a couple more factors. And it did. Overall, the factor loadings load on better. So it was easier to pull apart which factors loaded on which one. There wasn't a lot of cross loadings of any significance. So I moved forward with the 4 factors. And so in that case, so you can see what I originally did for the first 2. That's what I called them. I did a verbal intelligence and nonverbal intelligence, and those were the tests under those 2. So then I went to move forward with the confirmatory factor analysis with just the 2-factor model to start. So verbal and nonverbal. And then ran a summary. Here. So originally I did both, one with it going ahead and what's it called?
Factor loading.
Having it set for the factor loading.
Yeah, you
That's
missed the
one.
loading, so you missed the.
Yeah.
Yeah.
Up here, yeah, it should be
yeah.
factor,
Yeah.
factor loading. So you can see that. Then ran the fit measures. everything was kind of under where I would want it to be. You know, Tucker Lewis was under what I would want. Same kind of, you know, the CFI was kind of on the edge there. Let's see what was the other ones.
CFI, NFI.
RNSA, there we go. Is over even 0.08 for even acceptable, not under 0.05 for good fit. So between all those together, taken together, the model as a whole was a pretty poor fit. Then I did the variance set to 1 instead of the factor loading set to 1. And it came up predominantly kind of the same way. So we can see now that all the factor loadings were freely estimated. But again, if we look at all the fit indices, none of them were really indicating a strong fit model. So that's all summarizing this. So I talked about what my criteria were for it. You know, there were a couple that did meet some of my criteria, but as a whole, the model didn't meet the majority of what I would want to see. So I would not use the two-factor model if I was actually doing a paper. I would say this is a poor fit. So again, based on what I just know and then out of curiosity, I went with the four-factor model CFA just to see what it would look like. And here I added 2 subtests. So I broke off a couple pieces that, again, this is kind of just based upon my theoretical knowledge around psychology, the processing speed and working memory. Under those, I had coding and symbol search and digit span and arithmetic. So I pulled a couple of those away from the verbal and nonverbal. And then ran my model again with my factor loadings freely loading, or being freely estimated. And then when we look at, so I'll scroll down, the actual model fit then, it's actually a pretty strong model fit. So the overall model was significant. The GFI was greater than 0.95. Tucker Lewis was 0.952. Our RMSEA was 0.057. There we go. RFR was 0.039. CFI 0.963. So all indicating really good model fit for the 4 factors. So that's why, in the end, come up with the 4 factors, even though the original C-plot and my eigenvalues only showed 2 latent variables. I chose to focus more on the theoretical underpinnings for that, for the 4 model analysis. Is that okay? I'm not necessarily explaining things in my rationale for
Thank
things.
you. Actually, I do have a question. Why do you jump from 2 to 4?
Yeah.
So that's my question.
Yeah, so I don't have a good, it's not from a statistical analysis, I don't have a good reason for it.
Okay.
From a, having worked with the WISC and knowing what it's measuring, so theoretically, I know what it's supposed to be.
Okay.
And that's why I was able to pull that and say, I know there's actually more to this.
Okay.
So my justification would be, hey, in theory, I know from research that this should be, that this should have more factors than what only came up with the original eigenvalues.
Okay.
But the eigenvalues themselves, right? If I didn't know all that, yeah, I mean, I wouldn't be able to. I would have gone with that if I didn't have that prior knowledge. Because yeah, the cutoff. I mean, all these are under the cutoff that I would want to see.
Good. Thank
So
you.
that's my
Okay,
interaction.
good. Okay. Actually, that is correct. If you look at the original WISC test, there are 4 indicators. But for this data set, I make it a 2 because I did some observations. So that factor, if you really want to conduct that factor data analysis, factor modeling analysis, it cannot support the 4. Yeah, it just supports the 2. So that's why I think that in real data analysis, it's very tricky. So you're gonna respect your data, you're also gonna respect your theory. So if you choose 2, that's totally fine. It's fine because based on the data, so it just suggests 2. But you can also do some adjustment. You can just modify the number of factors a little bit. It's also okay. So it's kind of like there's no clear answer for this question. So in reality, it's very complicated. If you really want to respect your data, if you don't think about your theory, then it's just two, okay? But sometimes, maybe you can think, okay, so especially when you look at the factors. So I think that there's a, Yeah.
Sorry.
Yeah, when you have two factors, so
It's
uh,
two.
yeah, if you have two factor models, so I think one math test kind of like belongs to the verbal group. So it's not. Anyway, so my point is that you should respect both statistical data part and the theoretical part.
I have a question.
Question, yeah,
Yeah.
yeah.
Wait, so how did you said you added two more
Mhm.
factors in there
Yep.
that were not part of this original thing, right? Oh, I see. So then when you did that, it became a better model.
Yeah, it did. So when I did that, so we'll look at like the factorials, because I ran even just the EFA with that.
Yeah, so
And
how
as a
did you-
whole, it parsed it out better, where there weren't as many cross loadings, and there were, everything kind of met over that 0.32 loading. Outside of this one, I mean, we could argue that could be dropped there.
Because I was
because it-
wondering, like, because I cycled through 3 and 4 as well, but I didn't get. I was like, no, it obviously looked like 2 was better. But if you're saying like theoretically, you knew that 4 was going to be good. How did you even like create like another like piece of factor without changing the data?
Well, the data's already loaded.
The
so
same data
It
set.
was just coding.
Oh, we just run 2 models, 3 model, 4 model,
Okay.
yeah.
Yeah.
The data
You already
is
had
fixed.
that.
The data is, yeah, the
Okay,
data
yeah.
set is fixed. Yeah. Thank you. Great job. Yeah, thank you.
Good job.
Yeah. So I also want to invite Jack. Could you please come here, Jack? So he also run multiple factor models. So let's look at his solutions. Yeah.
Yeah, so I first stage like 4 factors should be kept. And since we have introduced reuse, and if we use the cases rule, that is that is how we get like 2 factors should be choose. Because 2 factors are larger than one in the graph. So, and if we use the parallel method based on the plot, 2 factors remain in the model, same thing. And if we use the cumulative method, the first 6 eigenvalues account for 80% of the total variance. However, 2 will be too small because there are 13 observed variables, and 6 might be too large. So we might like consider a number between 2 and 6. So next, I'm comparing the results by choosing different numbers of factors remaining in the model. And so if we use 2 factors, the p-value of the chi-square test is very small, so we will reject the hypothesis that 2 factors are sufficient. So 2 factors are not good. And if we use 3 factors, the p-value of the chi-square test is also very small. So same thing, we reject the hypothesis that the 3 factors are sufficient. Also, some variables cannot be arranged clearly among 3 factors, even with different rotations, and we can check the tables with different rotations, and some factors, some variables cannot be like distinguished clearly. So here I think 3 factors is 3-factor model is also not good. And if we use 4 factors, the p-value, is good. It's larger than 0.05, so we cannot reject the hypothesis that the 4 factors are sufficient. And by using the oblique rotation method, all the 13 factors could be divided easily among 4 categories. So 4 factors are good for the model. And if we use 5 factors, the p-value of the chi-square test is good. So we cannot reject hypothesis. But compared to the model with 4 factors, 5-factor model is acceptable, but it is more complicated. So because of the simplicity, we prefer the 4-factor model. And what's more, after I tried a different rotation method, oblique rotation method is still the best for the 5-factor model. However, I think there's a typo here. Should be the only one factor is correlated. Only one factor is correlated to the variable means. So there might be problem like to arrange this observed variable means, and also the variable picture completion cannot be distinguished clearly from the factors. So yeah, they might be have like similar like pointed, yeah. So we cannot distinguish clearly. So I think 4-factor model can be easier to interpret. So based on the interpretation, 4-factor model is also better. So in summary, based on the combination of interpretability, model fit, and parsimony, the 4-factor model is the best choice. So.
And you can also show the code and the result. Yeah.
The code. I
Yeah,
paste
he
all.
did a lot. He did a lot of like analysis, different models, different rotations.
So I will just show like compare the 5-factor model with oblique
Oblique, yeah.
oblique rotation. So I think this is the last oblique. I think this is results of 5-factor with oblique rotation. So maze here. So there's only, so for factor 5, all other observed variable are already like categorized, but there's only one observed variable for that is correlated to like can be arranged to factor 5. So that might be a problem here. And also for picture complete picture, I think it is this one.
No, the next one. After coding. Pick a range.
Pick
Pick a range.
pick a range. Right. So for this one, so for factor 1 and factor 2, they are they are very this one, factor 1 and factor 5, they are very close. So we cannot distinguish if picture arrangement should be categorized to factor 1 or factor 5. So that would be another problem. And however, for the oblique rotation with 4 factors, let's see here. For factor 1, we have information similarities, vocabulary, and the comprehension. And factor 2, clearly we have picture completion, block design, and object assembly, and maze, missing. And factor 3, we have coding and symbol search. And factor 4, we have arithmetic and digit span. So we have like used all of these observed variables. So this is clear, much more clear than the 5-factor model. Also, it is simple. So 4-factor model should be better than the 5-factor.
Good. Yeah. Any question? So some of you might give a 2-factor model. Some of you answer the 4-factor model. I all think that they are great. Okay, I give you 10 points. But so that's why when you do the real data analysis, it's not so easy. There's the single model which is correct. You may have this one and that one. So you can do some comparison, model comparison. So yeah, so Jared did some comparisons between the chi-square, right? Chi-square is very important, but also chi-square is very tricky. Because he ran the 2-factor model, 3-factor model, 4-factor model, 5-factor model, and then finally he chose the 4-factor model and the 5-factor model are best because the chi-square is not significantly different. It's not significant. But in reality, it's really hard to get those good results. In most cases, it will be significant. So sometimes people just use this. So I'm sorry. Yeah, thank you. Good job. Yeah, thank you. Yeah. Sometimes people use this index to do the comparison because the chi-square is always, in most cases, it's always very small. It's close to 0. So it's significant. But how can we handle the chi-square? So some people suggest use this index and to compare with, some people suggest 5 and some people even suggest 10. Okay. So that's good. In our case, we have the 4 or 5-factor models can have the non-significant result, but in reality, maybe we're gonna use this version instead of the original chi-square. Anyway, so he conducted a lot of like data analysis and different models, and also think about each detailed item of this test. Okay, for example, maze, yeah, and or for example for picture arrangement. Sometimes we need to do some modification by deleting some items or maybe combine some items, because based on the data analysis, some items maybe this one, okay, all the loadings are less than 0.3, something like there's a lot of cross loadings. If you want to keep the structure, factor loading structure simple without any cross loadings, then you can just think about deleting that item, okay? But of course, if you think that item is really important, you cannot delete them, then just keep that. And you can say that, okay, that item is partially determined by factor 1 or 3. So which one? 1 or 2, okay. And partially determined by factor 2. So that means when they design that item is not a single factor correlated. So it's determined by multiple factors. It's still okay. Anyway, you need to make a story. So you need to talk about these detailed items. Yeah, question. Yeah.
What would your tip or suggestion be when to eliminate a factor then? Like if there's only 2 or 3 that are loading onto this factor, when do you decide to like, this factor is not gonna, if there's only 2 items on there, 3 items on there, 4 items on there?
That's a good question. I don't have actual answer for that. Yeah, it depends on your design. Sometimes think about some very, very famous designs. Sometimes you have 8 items or 9 items, but still people use that because they have 8 items to measure the same thing. So Jia also mentioned that, okay, maybe the number of items is not so reasonable, so we needed to consider another model. That's also another consideration. That's also a good consideration. But in some cases, we just don't consider the number of factors. We just based on the data analysis and decide 2-factor or 3-factor or 4-factor model.
Okay.
And when you do, after you do the rotation, if the some items does not make any sense, then you need to change your model to another one.
Like
Yeah.
if you only have one item that's having a factor. with
That's
that,
not good.
That's not, yeah.
If there's a one item only correlated with one factor, then definitely you need to delete that item because that's not necessary to run a factor model. If that item can show, it can represent itself, then just use that item. No need to do the factor
Oh, I see what you
model,
mean.
yeah.
Okay.
At least 2 or 3.
Okay, so that would
Yeah.
be a good tip, like 2 or 3 in a.
2 or 3 will be good, and the 4, 5, 6, even 8, 9, it's still okay. Yeah, although it's not good because sometimes if you have unbalanced number of factors, you may have convergent problems. You may have some measurement errors when you do the data analysis. But if you have very good result, if you don't have any problem, then it's okay. Just keep that way. Yeah. The number of items is, you can think about that way, but it's not very important for our data analysis. Yeah. So actually, this is quite close to our real data analysis. So you may have like this model, you may have like that model. So you need to do some modification or comparison or respect both parts. Okay, the theory part and the data part, and do a lot of like consideration and decide that is your model. Yeah. It's not, okay, only that model is allowed. That model is wrong. No, not that case. Of course, in our class so in our lecture, I use a very good example. So in that example, we can clearly know the pattern. So we know that the verbal or we have 4 factors. Yeah, that's a good example. But in practice, in reality, we don't have such good luck. Yeah. Okay, so what time is it now? I think it's almost, it's almost 8. Okay, let's just do the multiple group analysis next week. Okay, so today that's it. So any question? And also, so in the beginning, so when Harrison tried to do the item decomposition, I asked him, okay, which matrix? Because I'm gonna mention the cycle package. So we have different package. So there's a famous package called psychology psych package. So there's a different options for you to choose. If you choose factor analysis instead of the PCA, right?
Yeah.
So they do the item decomposition based on the common factors part, commonality part, not the whole original raw matrix, correlation matrix. But the question is that, okay, we needed to start from the very beginning. Just cheat the, so here, I think it's correlation matrix. In the very beginning, we had the correlation matrix of the raw data. It's here, okay. Yeah. So it's where's that? Correlation matrix. Factor. Where's that? Where's that? Correlation. Oh. Oh, this is JAR's work. Where's the, here, JAR, I have a question. Where's the vector? Yeah, so this is a correlation matrix, okay? So, but I didn't, it seems that you didn't include, I'm sorry. You didn't include the calculation of this matrix, okay? Yeah. So from here to here, there's some code to get the correlation matrix of the raw data, okay, with the data, okay. That is the original raw data. So do the eigen decomposition based on that raw data, okay. Otherwise, you may have only one single factor model. So that's not a good model. So anyway, each of you, everyone did a great job. And if you pick 2, if you pick 4, or even you pick 3, I think all are good because you have some evidence to support your conclusion, to support your model. Okay. That's good. Okay. And that's for homework 4. And you will have homework 5 to do. Yeah. And thank you. Yeah. Thank you. So that's all for today's class. Yeah. See you next Monday.
I'm gonna meet with Dr. Wu tomorrow and get the raw data, because I can't find my,
Okay.
and then I'll talk to him about the latent variables.
Okay.
But what I was
Yeah.
proposed.
List up. Do you think about the first step? Okay. List all the possible variables in your model, and make a note. Okay. Are they observed, or are they latent factors, or some other variables? Yeah. Yeah.
Because you were talking, go ahead.
Yeah. You go ahead.
I just want to say hi.
Yeah. Yeah. I want to. Yeah. I'm okay. Good. Good. You look fine.
Actually, not.